Hi ladies and gentlemen, let me wholeheartedly welcome you to the fourth session on ECT 204 Signals and Systems. Today we will see the sampling to obtain discrete signals from continuous signals. So the title of today's presentation is Discrete Signals from Continuous Signals by Sampling. The contents of today's session are your learning outcomes, then a continuous signal to discrete signals, then sampling of continuous time signals. We will see the sampling theorem by Nyquist, then analog to digital conversion, and the summary of understanding. First, your learning outcomes. The first outcome is you will learn to generate discrete signals from continuous signals by sampling. Then you will learn sampling theorem due to Nyquist. Then you will understand the reconstruction formula. Then you will learn the process of quantization and analog to digital conversion, or ADC. Most things in nature are discrete, like you have, say, 10 apples, 4 oranges, so many boys, so many girls. So many things in nature are discrete. But most of the signals from transducers, like cameras, then microphones, etc., are continuous. Seismic sensors, they are all continuous in nature. So they give out infinite number of real values in any small interval of time, delta t. Now the question arises as to whether all these infinite number of values are actually needed to represent the signal, or can we represent the whole signal with a fewer samples. So if so, how many samples are needed to represent the continuous time signal faithfully? So now the question is, instead of sending all these infinitely many real values, is it possible to send fewer signals and reconstruct the signal faithfully? Now the answer is provided by sampling. So what sampling does is you can take samples of the continuous time signal x of t that is band limited from minus fm to fm. You can see, I assume that it's a low pass signal that is band limited from minus fm to plus fm. What I can do is I can sample this signal by multiplying it by an impulse train of frequency fs equal to 1 by ts. So the resulting discrete signal will be available for every ts, like 0 ts, 1 ts, 2 ts, etc. So of x of n ts, that is xt times st. Okay, I will show you how this is done. This is my original continuous time signal x of t. I have taken it as a sinusoid. This is my continuous time signal xt. Now I multiply this signal by a train of impulses. We have seen this train of impulses in the previous presentation. So if I multiply this signal by this signal, what I do is I get samples of the first signal, samples of this continuous time signal. You can see that these impulses occur for every ts, every sampling interval, 0 ts, 1 ts, 2 ts, etc. So I get the samples of this signal here. Here I have one sample. Here I get another sample of this continuous time signal. Here I get the third sample. Here I get the fourth sample. This is my fifth sample, etc. Now this, so that is the meaning of this equation 1. That is, the sampled signal x of n t is obtained by multiplying my continuous time signal xt with the with the impulse train s of t. This s of t is nothing but a train of impulses, that is I from minus infinity to plus infinity delta t minus I ts. So here you can see that I have taken 8 samples out of a period. Here I have 4 samples here and 4 samples out of this period. So out of every period of the continuous time signal, I have taken 8 samples. I can take a different sampling frequency and obtain here, say 6 samples here. Here I have taken 6 samples out of a period. Here you can see that the spacing or ts is greater. The sampling interval is more, so I get a fewer number of samples. Here I take 6 samples out of a period. Now the question is, what is the minimum number of samples? The fewer are the samples, the better it is for me. So now the question is, what is the minimum number of samples I have to take to faithfully represent the signal? Now the answer is provided by Nyquist sampling theorem. So by Nyquist sampling theorem, if the highest frequency of a continuous time signal xt is capital Fm, and if it is sampled at a rate fs greater than or equal to 2fm, then original signal xt can be exactly reconstructed from the samples using the interpolation formula. This gt, that is equal to sine 2 pi fmt by 2 pi fmt. This is basically a sinc function. So this is the formula for reconstruction. So if I take more than 2 samples out of a period, then I can faithfully reconstruct my sampled signal. How do I do that? I do this by passing the samples through a reconstruction filter whose response is sine 2 pi fmt by 2 pi fmt. I will come back to this topic again after I discuss convolution and everything. We will come back to the reconstruction formula. But understand this reconstruction formula is also part of the Nyquist sampling theorem. So right now I am not going into this low pass filter. We will discuss certain things like discrete convolution and all. Then we will come back to this. We will revisit this topic later on. Now, what the theorem says is if you take 2 or more samples out of every period, the original signal can be reconstructed faithfully. Now, if I take only 2 samples, one problem is it can be reconstructed, but the problem is if the sampling happens to be at the 0 crossings, then the reconstruction is not possible, because I will end up with no samples at all. Because if the sampling happens to be at the 0 crossings, then all I get will be 0. So that is why there is a greater than or equal to sign in the theorem. The reconstruction is done by the interpolation formula. We will come back to this formula later. This interpolation is equivalent to passing the samples through an ideal low pass filter to get the reconstructed signal. And now what I do is after sampling I get a discrete time signal. Now I can quantize these samples in magnitude also. Then the sampled signal become discrete in both time and magnitude. Such signals are called digital signals. The process of sampling followed by quantization together, I have my analog signal here, xt coming here. I do the sampling first and then the quantization then. So what I get at the output, it is called a digital signal. So, and this process of sampling and quantization followed by sampling, that is called analog to digital conversion. Then when you come to the end of this presentation, you learn to generate discrete signals from continuous signals by sampling. So what is sampling? I multiply my continuous time signal by a sequence of impulses or a unit impulse train to get the samples. So then the question is how many samples I have to take out of a period. That was provided by the sampling theorem. So that theorem says that if you take more than 2 samples out of a period, the original signal can be reconstructed. How can I reconstruct the signal? That is by passing the samples through a reconstruction filter, which is an ideal low pass filter. Then you understood the reconstruction formula. Actually, we will revisit this topic later on. Then you understood the process of analog to digital conversion. And that is the end of this presentation. Thank you all.